talking about converting decimal to binary last time. So we kind of went over this method a little bit of when we can take a number, and then if it's odd, we can put a 1 at the end. Let's see, right here. So 13 is the number we're trying to convert. And since this is odd, we're gonna divide it by, we're gonna subtract by 1, so our 1's here. And then 2 times 6 is 12. So like this, you see how this is equal to 13, right? And because this is odd, this is why we're giving the 1 here. And this is even, so we have a 0 here. This is odd, a 1. This is also odd. And so we have these numbers here, the 1s and the 0s. So we can look at this chart a little bit, and then we can try to do some examples. Do we have to turn our camera? I would like you to turn on your cameras, but so I could see all your faces. That'd be cool. All right, awesome. Okay, so does this kind of make sense? Are you guys ready for an example? All right. So we're gonna do this first one, 76, convert this to binary form. So does someone want to try this? You can get on your microphones, type in the chat. I can see someone drawing, but I don't see anyone on the mic. So, all right, I'll help you all with the first one, but I want you guys to do the next one, because this is fun. Like, we're just converting it to binary, which I think is a really interesting thing. So is 76, is this odd or even? This is even, right? Yeah. So 76. Ooh. Let me get this working real quick. So yeah, 76. That's equal to, it's an even number. So it's 2 times what is 76? So 76 divided by 2 is 38. Perfect. I see someone in the chat. Thank you. And then are we gonna add a 0 or a 1? Oh, someone has a full answer. Let me see. You're very close. I think you have 1 extra 0 on the end. But if you'd like to get on the microphone and explain why you got that, I'd be very happy.
So it's like 76 is like 64 plus 8 plus 4. And that, so like 64 is like 2 to the 6th power. 8 is 2 to the 3rd power, and then 4 is 2 to the 2nd power. I might have miscounted how many zeros I have in here though.
That's a really interesting way to do it. It's different than our little method up here. Well, but I think yours, I think it works. I like that a lot. So let's see. But if we're using this method, we're gonna add a 0, right? Because it's even. And we can keep doing this, right? So we can take this 38, we put that here. And that equals what? It's 2 times 19. It's even, so we add a 0. And then we can bring this 19 down. That's going to equal, so now we have an odd number, right? And so we can't divide this by 2. So we have to bring this 19, we have to bring it down 1 number. So we're going to use 18. So 18 divided by 2 is 9, right? And since we subtracted a 1 earlier, we're going to add a 1 in the end. So you see how we're getting these 0s and 1s here? This is what we want. This is the binary number forming in front of us. All right. So we're going to use this 9 down here. So it's 9. It's going to be equal to 2 times 4. So I'm starting to remember. Awesome. I'm glad. Okay. So now we're going to bring this 4 down here. this is going to be equal to 2 times what? 2 plus 0. And then we can bring this 2 down. 2, and that's 3 times 1, right? So we're getting there. We have 0 here. And then finally, we bring this 1 down, which is 2 times 0 plus 1. All right, so now we have zeros and ones here. And the weird thing about binary is we're reading this backwards. So we're going to read it, this way. So if we're going to write out the binary form of this, 76 is equal to, starting from the bottom, so 1, 0, 0, 1, 1, 0, 0. Awesome. I see some people in the chat. Amazing. All right. So how is that, everyone? Does that start to make sense? See people nodding. Awesome. All right. So what about this next one? Does someone want to try that one? Or does anyone have any questions about the first one? So I'd be happy to answer them. All right. So we're going to try to convert 193 to binary. So can someone get on the microphone and help me out with this one? It's gonna be the same. Oh yeah, thanks.
Okay.
Good.
So first you would have to divide 193 by 2. 193 by 2, and you get 2 times 36 plus 1.
Awesome.
And then you would do 36 divided by 2, and you would get 18. So 2 times 18 plus 0.
Perfect.
And then the next one is 2 times 9 plus 0. And then 2 times 4 plus 1.
It's back real quick because I'm double checking the math. So you said that we had for that first one 93 divided by 2. So I think it's not 36. I think this is a 96 up here actually.
Oh, I'm sorry.
Yeah, you're good. I love the participation. It's all good. But let's redo this real quick.
Okay.
Because you're doing really well.
Thank you.
All right.
So 96 divided by 96 times 2 plus 1. And
Perfect.
then it would be 2 times 48 plus 0. And then it would be 2 times 24 plus 0. Then it would be 2 times 12 plus 0. And then 2 times 6 plus 0. And 2 times 3 plus 0. And 2 times 1 plus 0 plus 1, sorry. Plus 1. And then 2 times 0 plus 1.
Awesome. So let's see, there's an extra. Can you guys see if I go off my slide there? Well, she said it. So let's see, plus 1. Perfect. So now how do we read this? We read it backwards, right? So we can read out this final number.
It'd be 1 1 0 0 0 0 0 1.
Awesome. Look at that. That was fun, wasn't it? Because like that's a big deal. Thank you so much for helping. Because yeah, we can just convert a decimal number to binary form. And I think that's pretty exciting. So let's clear this. And let's go to we have 2 more. Let's see. All right. Does anyone want to help me out with these? We're gonna do 97 yet next. Let's see, can someone get on the microphones?
Can I try?
Yeah, definitely.
All right, hold up. My microphone was off. So 97 divided by 2, you won't get an even number. So that would be 48 because you want to subtract 1 from the 97, so it would be 96. And the 90 or not 96, sorry, 48 divided by 2, that's an even number that comes out as, hold on, let me check. Comes out as 24. 24 divided by 2, that's an even number, so that comes out 0, and that will be 12. 12 divided by 2 is an even number that comes out as 6, which is a 0. 6 divided by 2, that comes out as an even number, so that's 0, so that's 3. And then 3 divided by 2, you can't really do that, so you have to subtract 1, so it would be 2 divided by 2, and that would equal 1, which is a 0. And then 1 divided by 0 is just a 1 because you can't really do 1 divided by 0.
Perfect. All right, so you want to read out that binary number?
Sure. So it would be 1 1 0 0 0 0 1.
Perfect. Look at that. That wasn't so bad. Nice. Thank you for helping. All right. What about this last one? 255 is a big one.
Can I try again?
I see someone raising their hand. So let's go to Ryan. Give you a chance.
Okay, so straight away, I already see something kind of strange, which is like 2 to the 8th power minus 1. Also, if we were to do it this way, it would be like 2 times 127 plus 1.
So can you repeat that? It was 227 plus 1, you said?
2 times 127 plus 1.
Oh, yeah. Awesome. Write it down here.
2 times 63 plus 1.
Mhm.
2 times 31 plus 1. 2 times 15 plus 1. 2 times 7 plus 1. 2 times 3 times plus 1.
Mhm.
2 times 1 plus 1. And 2 times 0 plus 1. So it's just all ones.
Yeah. So you want to read that out?
1 1 1 1 1 1 1 1.
Perfect. Look at that. Awesome. So I really liked this section because it's combining, modular operators like that, but we're actually doing something really cool. We're doing decimals to binary and binary to decimal. This is really important. I think this is a really cool lecture. So, let's see. That's all. Let's see. That's all from binary operators. So I hope you all enjoyed that. And now I'm going to pass this off to my good friend Jess. She can teach you all about sums.
All right. Hi, everyone. My name is Jess. Let me get my screen shared. Okay. And present. All right, so that was a great segue by Gray. Thank you very much. Today we're going to be talking about sums, and I know that this like seems like such a basic concept. Like it was kind of one of the first things that you guys learned in school, right? Is how to add like 2 + 2 and 1 + 1 and all of that stuff, right? And you guys, I've already seen you've done like a lot higher stuff just working with Gray, but there's some really cool applications when it comes to sums, and we're going to see kind of a cool twist on sums that you might not have ever thought about before, which you actually might see in your classes or in future classes. So, okay, so let's get started. Okay, so first things first, we have this cool triangle right here, okay? So let me see if I can annotate. All right, I want you guys to, let's go down the line, and it'd be really cool if I could have like a different person unmute their mic and let me know what the end of each row equals. I mean, of course, if you want to go first, kind of a gimme, but can I get someone to unmute and let me know what the first row equals?
1.
1, yep, perfect. Genius answer. Okay, what about the next row?
Yes.
3.
Yeah, 3. Very cool. Okay, next.
6.
6.
Okay,
10.
10.
15.
15.
21.
1.
28.
Claudia.
36. 45.
55.
55.
all right, awesome. I heard a lot of voices there. That was great. Great. Thank you for the participation. So we can kind of see the pattern here. This section right here, all the red numbers that I just wrote, which I think is further explained on the next slide, but those are all called triangular numbers. So I want to show you guys the visual of the triangle, and we'll talk about like kind of what it means to be a triangular number. But we see that each time we go down the row, we're just adding the next integer to the previous row. So we start with 1, and the next row we add 2. And the next row we add 3 to that number. And the next row we add 4 to that number. And we go on and on and on. Okay? So let's see what the actual application, what this could mean. Okay, so what is a triangular number? So let's build some intuition here. So let's actually like visualize what we did on the previous slide, because I kind of already had it in like this big triangle form. But if we look at each individual number that we summed up at the end, we see that they all kind of form a triangle of their own, which is really cool. So it's kind of like a big triangle filled with smaller triangles. So we see that this one, obviously, I mean, it's not really a triangle, but it's just kind of by itself. So it's like, think of it kind of as the tip of a triangle, but 1 is considered a triangular number because it's at the very peak of our triangle. And then when we have 3, we can just add these 2 points underneath this 1, and then we have a triangle. And then each time we're going to add the next number underneath, and we form all of these separate triangles. So I don't know if you guys have heard of this before in school, but I think it's something really cool about math that a lot of times they don't really teach you, but I think it's just a cool concept to think about, the fact that there are certain numbers that form triangles of their own. And when you push them all together, they form even bigger triangles. So let me see if I can clear this. Okay, so what if we wanted to find the 100th triangular number without like doing all of the addition by hand? So on the 100th row, we would have the sum 1 + 2 + 3 + 4 + 5 all the way to 100. Okay, so when we looked at the smaller triangle, it was a lot easier to just do that in our head, right? We would just like add the next number and go from there, but it would take us probably a good, maybe 2 minutes. So it's not terrible, but if I wanted you to calculate the 576th triangular number, that would be very extensive for your time, right? But there's a cool way, and I'll show you how we can do this by hand without having to calculate all of the sums. So Let's just observe just the pattern. So maybe if we can figure out how to do this and segue into the formula that we will be using. Okay, so let's observe the pattern. So can anyone unmute and let me know what they're like, what you guys could maybe see as a relationship between this figure right here. So the number of dots in the figure and 1 plus 2.
1 plus 2 equals 3, and there are 3 dots that have a different color. So like 3 blue dots and then 3 purple dots.
Yeah, exactly. That's a great relationship. Does anyone see anything else? Like there's no like wrong opinions here, but does anyone else see a different relationship, or is that what everybody was already thinking? Okay, I don't hear everyone, so I'm assuming we're all kind of on the same page here. So yes, that's a great point. So we can think of this as 1, and then this is 1 plus 1, so that equals 2. So we can kind of separate our blue dots and our purple dots and think of it as 2 kind of groups of 1 plus 2. Right? So how many dots total do we have?
6.
6, exactly, right? So that is the same thing as just saying 2 times 3 equals 6. Okay? So not really any crazy questions or calculations with this, but this is kind of getting us started. And we'll see that this leads into even bigger and better things. Okay? Okay, so yeah, sorry, this is just another visual. We see that this is a 1 plus 2. So like 3 little dots, and the other ones are other 3 little dots. And when you form them together, then you get the whole figure that we just looked at. Okay. So how about this? Let's extend our thoughts even more. So what about relationship between this figure and 1 plus 2 plus 3 plus 4? Okay, I see a hand raise from Erica and Kai. Either of you guys want to go?
Yeah, so what I see is that like this, like the other one, this is just 2 of the same triangles, and if you separate both triangles, it would equal 1 plus 2 plus 3 plus 4 times 2.
Yeah, that's exactly correct. So yeah, we can kind of all think of these as like their own individual dots, but when you add them together, of course. Sorry, it's gonna take me a long time to write okay, so we have 1, 2 dots in this row of blue, 3 dots in this row, and 4. So if we add all of those together, then we would get however many blue dots there are. Which, can someone tell me however many blue dots there are? And or purple, same amount.
10.
10. Cool.
10 plus 10
So
equals
we
20.
have, yeah, exactly. 10 plus 10 equals 20. Or you can think about it as 2 times 10 equals 20. So 2 different perspectives, but both
That
work.
too.
Both are math. Yeah, exactly. So I have 10 here, 10 here, and then we could actually write it in kind of like 3 different ways. We could write it as 10 plus 10, which equals 20, total amount of dots that we're looking at here, or 2 times 10, which both of which I just said. But we could also write it as 2 times 1 plus 2 plus 3 plus 4, which equals 20. Or 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4. Okay, so kind of gets tedious as we go on. And I know I'm asking you all the little tedious details, but it's important to look at this stuff, kind of get down to the nitty gritty so you understand everything as we go along. Okay.
Just an example, I mean, I can kind of see this as like sequences and a pattern in a way. So like 1 plus 2 plus 3 plus 4 plus 5 and so on. Just a
Yeah, I mean,
fact.
You're hitting it right on the head. Like we're getting there. So yes, this is a little segue. We're gonna get into something called series today. So which is very like closely related to sequences. So we won't really touch on sequences, but we will see like at the very end of this presentation, we're gonna like do some really cool series. Okay, so let's get there. So we can look at some cool math. Okay, this is just a big presentation of the visual. It wouldn't fit on the last slide. So we can think of this in this way too. We just separate them in half figure out each half, and then if we mush them together and kind of figure out how to calculate 1/2, then we can calculate both. So, okay, so in both of those examples, the number of rows is the same as the last number we added. Okay, so the number of dots in the rectangle is 2 times however many we had up to. So in the first one, we had 1 + 2. And then in the second example, we had 1 + 2 + 3 + 4, right? And we can go all the way up to whatever number. Of course, my computer screen will only fit a certain amount, but we can do the same visualization and we can do the same process for up to n numbers. So you could make n = 4, like our second example, or n = 1,000, and so on. Okay, so we can build this formula that will work in every single circumstance, no matter how big our number is. Okay, so in this case, let's think back to what an example that we just did. So let's pretend this is 1 + 2 + 3 + 4. Okay, so what is my n in this case? In the example 1 + 2 + 3 + 4.
4.
4, exactly. We're going all the way up to n. So my n = 4. Okay, so if I want to use this formula, instead of having like the pictures that I drew before, which of course, smaller the numbers, it's easier to draw pictures, but just to show you guys the example of the formula, we can plug in 4 times 4 + 1, which is 5, over 2. And we get 20 over 2, which equals 10, which is exactly what we just found. And we, of course, we could have just added 1 + 2 + 3 + 4. But again, if we wanted to have some crazy big number for our n, if we wanted to sum up 1 all the way up to 1,000, we could use this formula instead of just adding them all up on our calculator or just adding them all up by hand. So this is a really cool application. And I'm sure you'll see this at some point in school if you haven't already, but it works in every circumstance. Even small cases where you could add it up yourself, it works. Big cases, it works too. Okay. Any questions on this? Are we all good here? We saw an example being plugged in, but of course, throughout our presentation, we'll see a bunch of examples. Okay. Anyone that's copying this need me to wait, or are we all good here?
Pretty sure we're good.
Okay, awesome. Okay, so we talked about the sum 1 all the way up to 100. So now that we have a cool tool to calculate it, anybody want to unmute and try this for me using our newfound formula, our newfound tool to calculate a larger sum?
Jess, do you mind going back to the last slide so that they can they want to see the formula?
Okay, hold on one second. We'll get to this one, but this is the last slide. If any student needs to copy or anything.
Can I look at 100 times 101 divided by 2?
Yes, that's perfect. Athanasios, are we good on this slide? I don't know.
I think so. Yeah.
Okay.
Yeah, Angelina wanted to copy it. Yeah.
Okay, yeah, no problem. If you guys ever like need anything, I can see, oh, that's probably why I see the chat popping off, but I can't see it because there's a bunch of things going on. But yeah, if there's ever a problem, anyone feel free to unmute and let me know, or any GTAs. If I'm missing anything, please let me know. Okay, so yes, exactly what someone just said. There we go, perfect. Do you mind repeating that, and I will annotate as you explain?
Me?
Sorry, I'm not sure who was just explaining it the last time someone started to do this problem.
Oh yeah, so 100, so the formula is n times n plus 1 divided by 2. So we have to first figure out our n, which is 100. So we do
Awesome.
100 times 100 plus 1, which equals 101. 100 times 101 equals 10,100. And that divided by 2 is 5,050.
Divided by 2 equals 5,000. Oh, 5,050, sorry. Oh no, there we go, 5,050. Okay, are we all understanding here? I know only one person answered, but do we see the application with the bigger number? Because I only showed you up to 4, but this could work for 10,763. Okay. Very cool. Okay, thank you so much for the participation here. So, anyone else want to go ahead and try this next one? Not as big of a number, but you kind of do the same process.
I can do it.
Go for it.
Okay. So, 31 times 31 plus 1
Perfect.
equals 32.
Mhm.
So 31, can you still hear me?
I can hear you perfectly.
Okay. 31 times 32 equals 992. And if you divide that by 2, you get 496.
Okay. So let's do this divided by 2, divided by 2, divided by 2, which equals, say that one more time. What's the answer?
496.
496. Okay. Everybody good on this? Makes sense? Yes, okay. I'm checking the chat this time. I see some yeses, yep. Okay, perfect. I tried to throw in quite a few examples in here. I'm not sure how many I have, if there's another one on lock after this. Let me see. Oh yeah, okay, one more. Anybody else wanna present? Thank you so much, Rael, that was perfect.
Is it fine if I can answer this question?
Armand, go for it.
All right, so you gotta write the formula n parentheses n plus 1 parentheses divided by the 2. So then first to start, you have to multiply, oh wait, what happened to?
You're good, sorry, my pen was a little laggy. I hear you.
So then you would have to do 92 times, wait, what happened to the previous slide? I saw.
Oh, was this not the one?
Yeah, it was 92, I think.
Yeah.
Oh,
yeah,
I'm so sorry. Duh,
yeah,
we just did that
I was gonna
one.
say,
Okay, there we go.
I was gonna say, yeah, where was the 92? So 92 times the 92 equals 8,464. Not the 92. The 8,464 plus 1 equals 8,465.
Okay, hold on,
Yeah.
pause really quick. So, because I don't have like the math like written up there. So what two numbers did you multiply to get?
92 times 92 equals 8,464.
Okay, don't forget that we want to multiply that n. So 92 is our n. So then we want to add that 1. So we're going to end up multiplying 92 times 93.
Okay, my bad.
No, you're good. You're good.
So 92 times 93 equals 8,556. And 8,556 divided by 2 equals 4,278.
Okay, some really big
that's
funky
it.
numbers.
Yeah.
Cool. Do we all agree? Are we all good here? 4,278. Awesome. Very cool. Thank you very much. Okay. I think that was my last example. Okay. So, okay, yeah. So let's build some intuition by considering the following. So we looked at some examples, but have you noticed how they all have started at 1? Okay, so our formula that n times n plus 1 over 2, that works in every circumstance, as long as the first digit that you're adding is 1. Okay, so we could add 1 plus 2 plus whatever all the way up to 1,000, and we can use that formula. But if we are starting at a different number, so in this case on this slide, we're starting at 5 and adding up to different numbers. But if we're starting at a different number, we might need to switch our thinking up a little bit. Okay, so let's look at the 4 different things that are on the screen. Okay, so we have first 5 plus 6 plus 7 plus 8. So that's 4 terms, right? Same thing if we added a plus 9, it'd be 5. If we add a plus 10, it'd be 6. So something really important if we aren't starting at 1 is we need to figure out how many terms there are that we're adding up. Because if we start at 1 and we add all the way up to 4, it's very clear that we have 4 terms. 1 plus 2 plus 3 plus 4. In the same way, if we add 1 plus 2 plus 3 all the way up to 100, it's clear that there's 100 things that we're adding together. But if we don't start at 1, it's not so clear. Okay, so if we wanted to look from 5 plus 6 plus 7 all the way up to 24, there are 20 terms. But we can figure that one out by using this nice formula. Okay, so I will demonstrate how that works with this sum up here, the 5 plus 6 all the way up to 24. This is another really useful formula. So if you guys are wanting to participate in any of the examples, which I hope you do, it might be a good idea to copy this. So let me annotate while you guys are copying, and I'll demonstrate how this works. So we're going to take this last number in our sum. So in this case, 24. So we're going to take 24. We're going to subtract the first number in my sum, which it didn't start at 1. So that's the reason why we have to even use this, because we don't know how many there are. And of course, we could count this. That's definitely doable. Since it's such a small window, this one, we could count 20 times. But of course, the larger numbers you use, this gets harder to just count it. So minus the first number in my sum, which is 5, over the common difference. Can anyone unmute and tell me what the common difference means? Does anyone know?
I'm pretty sure the common difference is like the pattern of like the number being added or like subtracted throughout the whole equation.
Yes.
Sure. Yeah.
Yes.
I was just gonna say
perfect.
I wasn't sure for the first part.
Yeah, no, you're good. I mean, that's honestly kind of a hard question because we haven't really seen anything different than a common difference of 1. So do we see the difference between 5 and 6 is 1? The difference between 6 and 7 is 1. But we'll see later that there might be a different common difference. So if I want to add 2 plus 4 plus 6 plus 8, all the way
Common
up
difference
to
of 2.
Exactly.
Yeah.
All the way up to 36. In that case, it doesn't start at 1, and we have a common difference that's not 1. So those are all things that we need to consider here and try to figure out as we go. Okay, but in our circumstance right here, 5 plus 6 plus 7, the one that's on the slide, our common difference is 1. Okay, so we're just going to be dividing by 1 in our formula. Easy peasy. And then we're going to add on that 1 at the end. Okay, so does anyone want to tell me what that equals?
20.
20.
20. Yeah, spoiler alert, it should match. Okay, so in this case, you could just count it. So you can verify the math all you want to. If you want to just count 5 plus, like there's 1, 2, 3, all the way up, and count kind of like in between these dots, in between the ellipse. But there will be 20, and the more terms you have, this formula comes in real handy. Okay. Any questions on this? Because we will have to figure this out in order to figure out sums that don't start at 1. Okay. This is a little building block to get us up to a little harder stuff. Okay. Everybody got this formula? Speak now. Okay, perfect. Okay, so how would you calculate 5 plus 6 plus 7 plus 8 all the way up to 24? This last slide, I told you how to figure out how many terms, but I didn't tell you how to calculate it. So kind of the question that I already somewhat answered, does anything change when the sum no longer begins at 1? Yes, it does. We can't use our fancy formula. Does anyone have any ideas? You don't have to know. Does anyone have any ideas they want to share? Or if they want to just use their calculator and go for it, maybe we can double check our answer once we learn how. Does anyone have anything they want to share? Or if they want to go for it? Okay, no worries. I hear silence. It's okay. Because I haven't taught you how to do this yet. Oh, I see a raised hand. Erica or Kai, either one. You want to go for it or let me know your thoughts?
We proposed maybe to the beginning, for the beginning formula where it was n times n plus 1 divided by 2. We were proposing perhaps n times n plus whatever the starting number is, which in this case is 5 divided by 2.
Okay. N plus, you said first number? And then divided by 2?
Yes.
Okay. Very cool. Very cool idea. Okay, so let's actually see. I'm very happy that you guys said your thoughts because let me clear the screen. Oh, well, just kidding. We're not directly getting into that yet. Let's think a little bit more on that, but that's a really good idea. You'll see soon that that's a really good idea. Okay, so here's another way to think about it, just in case you didn't have that thought or you don't really know how to tackle this problem. So we did already kind of figure out how to calculate a sum or a series, which I'll further dive into later, but we already figured out how to calculate this. You could both just add this since it's a smaller amount, it's a smaller number. It starts at 1, so we could use our formula. Okay, but there's kind of another way to think about it. How is 6 plus 6 plus 6 plus 6 plus 6 related to this 1 plus 2 all the way up to 5? Anyone have any ideas?
It's the same thing except 1 plus 2 plus 3 plus 4 plus 5 has a common difference of 1, but 6 plus 6 plus 6 plus 6 plus 6 has a common difference of 0.
Okay, that's true. That's true. That's a very cool idea. Yeah, the common difference would be 0 here, and the common difference would be 1 here. Exactly. Okay, any other ideas?
I kind of observed this, but like if you add anything like forward, so like 1 plus 2 plus 3 plus 4 plus 5, and then you go from 5 to 1, so like plus or 5 plus 4 plus 3 plus 2 plus 1 is going to equal the same answer.
Mm-hmm. Yeah, so you
So
can
like,
think about it kind of both ways.
Yeah. So like 1 plus 5 equals 6, 2 plus 4 equals 6, 3 plus 3 equals 6. So there's like, how would I say, like patterns of like equaling a certain number. So that's how I kind of observed it.
Yeah, that's exactly true. Like we're looking at some different ways to just look at numbers that your teachers might not have pointed out to you. So it's kind of just increasing your mathematical intuition. So can anyone tell me what 1 plus 2 plus 3 plus 4 plus 5 equals?
15.
15? Okay. And what about 6 plus 6 plus 6 plus 6 plus 6?
30.
30. Okay. How is 30 related to 15?
Because 30 divided by 15 equals 2.
Okay, that's true. Any other relationship maybe? That is true. Yes. But maybe let's think about it the other way. We could see that 30 divided by 2 equals 15. Exactly. Okay, so again, we're just thinking about different ways to approach this because these come in handy because we need to use this kind of thinking when we are calculating like bigger sums that don't start at 0 and that have a different common difference than 1. Okay, because at the end, we're going to see all of those combined. Okay. All right, so exactly that. 1 plus 2 plus 3 plus 4 plus 5 is half of the number of terms multiplied by the sum of the smallest number and the largest number 5. So very, very, very close, Erica, exactly like what you were thinking. The number of terms is the only thing that was a little bit different than your formula that you proposed. So, and it gets a little confusing because we called them both n. So the number of terms we called n and the other one we called n, but remember there are 2 different formulas. So the number of terms, maybe number n instead of n, if that helps you. I'm not sure how you guys copied it down, but I know on the slides they are both labeled n. But yeah, our formula that we will be using is the number of terms times the first number plus the last number. So kind of like n and whatever your first number is divided by 2. Okay, you were so close. Like that was awesome without like giving any prompting or anything. Okay, so we can see this. And this is another way of thinking about it too, kind of similar to like the box. I call this the box, kind of like a box. We thought about that with the 1 plus 2 plus 3 plus 4 plus 5. But if instead we have a common difference of 2, how is this related to this? Oh, that was a weird squiggly. Anybody have any ideas?
The sum of 10 plus 10 plus 10 plus 10 plus 10, divide by that by 2 and you get 1 plus 3 plus 5 plus 7 plus 9.
Yes, that's exactly correct. And then if we divide by 2, sorry, that is 50, but if we divide by 2, we get this guy, which is 25. Okay. Cool, and we see that there are 5 terms in this right here, same thing right here. Of course, they're the same, but there's 5 terms. In this case, you can look at that, but we do have a cool formula in case it's not so clear. And then the first number plus the last number divided by 2. Okay, any questions on this? Just threw my stylus. And does anyone want to tell me in using this formula how we would get this 25? Like, how does that look in the formula? I know that we kind of just added them up, which you definitely could do, but in using the formula, what does that look like? Anyone want to tell me? And I'll annotate it. For this guy, if I want to use this formula up here.
$25.
Can I try?
The answer is 25. That's correct. Yeah, like very simple addition. We could have figured that one out. And I know that we already like figured that out before, but yes, Armand, if you want to go for it, like plugging this in to our
All right.
formula and then, yeah.
So following the formula, you want to have number of terms. So both problems have 5. So there's like 5 numbers in that equation. So I'm going to pick the problem 1 plus 3 plus 5 plus 7 plus 9. So you want to multiply 5 by 1 since that's the first number, and you want to multiply 5 by 9, which is the last number. So that would be 45. Now, then you want to add, what's it called? 5 plus 45, and that would equal 50. Yeah, and 50
Oh, I see
divided by
what you
2.
did. You
Yeah,
distributed this in. That's a cool idea. You definitely could do that. Mm-hmm.
and then 50 divided by 2 equals 25, which is the answer, of course.
45. And then we are dividing it by 2. So then we get 50 divided by 2, which, spoiler alert, we already know is 25. Okay. Okay. 2 ways to calculate it. You could just use your calculator. or now that you have a really cool formula, it will work in every case. Okay? So this first part is exactly what we just did, but I wanted us to do it on our own rather than me just giving us what it looks like plugged into the formula. But it's exactly what Armand just explained to us. We have that 5 times 1 plus 9 over 2. So 50 divided by 2, which equals 25. Okay, so what we were hinting at earlier is that this kind of sum that we've been working with is called an arithmetic series. Okay, that's kind of the whole process of what we're learning today. We were just breaking it down into chunks so that we would understand the process. But an arithmetic series is just summing up numbers as long as they have a common difference. Okay, so if the differences between any number and the next larger number in the sum are the same, AKA, that means that there is a common difference. So throughout the next, I think, couple of examples that we're going to look at, you'll have to determine if there is a common difference, if it's even an arithmetic series at all. And if it is, then we can use our formulas to calculate it. Okay, so this is the combo of everything that we've learned thus far. And I know I'm getting close on time, so let me see what this next slide has in tail for us. Does everybody have that formula copy? I know it was on the last slide, but are we all good there?
Pretty sure.
Okay. Awesome. Okay, yes, so we're jumping straight into some examples right here. And this is using everything that we have learned today to determine, number one, if it's even in an arithmetic series. So can we even use any of the formulas that we've learned? And if it is, find the sum. Okay, I'll give you guys like a couple seconds to just look at it, but if anybody does want to hop on the mic and give it a shot.
Can I give it a go?
Go for it.
Okay, so automatically there are 6 terms in the equation. So by counting it, you just know that's 6. I think anybody can know
Yeah,
that.
this one you didn't have to
So-
use any fancy formula, which is nice.
Yeah.
You just see number of terms equals 6. Okay, you can continue. Perfect.
So then you want to multiply 6 by the 4, since 4 is the first number, and that is part of the equation of the number of terms multiplied by the first number, and then the number of terms multiplied by the last number. And the last number would be 24, so you would have to multiply 6 by the 24, which equals, hold on, let me just calculate this, 144.
Calculator does come in handy. Okay,
Yes.
so we have
so we want to multiply 6 by 4, which is 24, and then of course 6 by 24, which is 144. And then 144 added with the 24 equals 168. And then you want to divide 168 by the 2, which equals 84.
awesome. Okay, so we kind of skipped over the first question. Is this sum an arithmetic series or not? Any ideas?
Yes,
Okay, what's your reasoning, Rael?
because like you can all, it's like 4, like 4 plus 4 equals 8, 8 plus 4 equals 12, and 12 plus 4 equals 16.
Exactly, so it's consistent. And I know that it might seem tedious to check, but if it's not super clear that the common difference is 4, because what if I decided to throw a curveball and at this very end, instead of 24, I wrote 25. If you don't check all the way through and make sure that the common difference is there, and of course, in this case, we don't really need the number of terms formula because you can just count that there's 6, but that number of terms formula relies on common difference. Okay, so if there is no common difference, that formula can't be used. Okay, so that's the importance of this. But yeah, You are correct, Rael. There is a common difference, and that common difference is 4. Okay. Any questions on this? I see that it is 3 o'clock, and I think I have 2 more examples in general. So I think we'll pick up next time. And we'll finish off this presentation. Let me stop sharing my screen. Dr. Kwan, do you have any words for them? I know they need to type bye with their name, but I didn't know if you have any final remarks.
Yeah, it was a very interesting session, right? And well, when you leave, you will type bye and with your full name. Thank you, Jess.
Yeah, thank you guys for all your participation. I really appreciate it. I hope to see you guys next week.